possibilities like primordial black holes and so on. So studying the evolution of the universe, considering that it was unified at the very beginning, one can come with different ideas of the possibility of studying very energetic processes and particles. So at the moment, the highest particle observed is about 10 to the 20 electron volts. And that tells us about the challenges of reconstructing this kind of primary particles in case of cosmic rays. So as you know, there are many candidates for dark matter. Some of the most popular are like the QCD axion, which fixes the strong QCD problem, or other related to a pre-inflationary epoch, or related with different hidden symmetries, extra symmetries that go beyond the standard model. Also, there exists the possibility of the creation of primordial black holes, which may have some constraints already due to possible Hawking radiation and so on. So all these kind of very energetic particles could be the cause of cosmic rays. But we know that some of those cosmic rays, especially the ones that are very commonly detected, are produced by astrophysical or galactic sources. For instance, if we consider the very high flux at very low energies, most of these particles come from the sun or are produced in supernova explosions or from pulsars. On the other hand, if we go further and further in energies, we will find more energetic processes like starburst in active galactic nuclei. But as we go further and further into energies, we know that we see that the flux of cosmic rays dramatically decreases. For instance, here, if we want to observe a particle of more than 10 to the 20 electron volts, the flux is so low that one will be able to detect one particle per kilometer square per 1,000 years. That means that we really need huge detector arrays that cover large areas. We also know that there are some constraints on the acceleration of these particles, and this is just from the electromagnetic processes. There are some limitations from the physics, the physics of these electromagnetic processes, and there's also the GCK horizon that may, if that is fully applicable, they may also slow these particles or make them interact with the different like the cosmic rays background, or like the CBM, cosmic microwave background, and so on. So this defines some sort of horizon. So there are limitations. That also points out that perhaps these particles either are some kind of relic of dark matter, or they are produced in a different way nearby. And a few of the recent studies may point out to very energetic processes like neutron star mergers that can emit very energetic neutrinos, but also at rotating black holes, like in the case of the magnetic Penrose process, where when a particle can gain a lot of energy by falling into the event horizon of a rotating black hole. That's to the ergosphere, not into the event horizon, and this particle may escape. For that, there are some works that have estimated what is the maximum energy that if this process exists, that can be available. For instance, here in this work of Arman Tursunov, he reports that an extremely rotating supermassive black hole of 10 to the 9 solar masses has a total available energy of 10 to the 74 electron volts, which is huge. However, this is unexplored. This is just theoretical ideas. It might be possible. So that's why we try to figure out how to study these exotic scenarios. The other possibility is that if there's a very energetic, ultra high energy photon and interacts with the magnetic field of the sun, it might create a shower that will cover basically the Earth, that will be at large scales. So in this case, we have done simulations to try to study the footprint that this kind of pre-shower, with pre-shower I mean showers that are created outside the Earth, may look like. And we have, for instance, used very simple approaches to considering that the magnetic field of the sun is a dipole or maybe just a quadrupole and things like that. But we found very interesting characteristics of this process. For instance, that the showers, the footprints will be elongated and the core will have rather a elliptical shape, and this is one of the characteristics of this scenario. When we think about showers, extremely extended showers that will cover beyond a region on the Earth, but for hundreds of kilometers, we need to think about going higher than the current observatories, which, by the way, are really precise and they are doing very well. Then we need to come with a different approach, and in that case of a generalized detection of cosmic rays, when the plasma cosmic ray doesn't only leave an imprint that is localized, but instead it creates something like a collection of showers that ends up being called or being itself a cosmic ray ensemble. Then there's a possibility for a unique signature, which might result in correlated either in time or in space or both events, and that could give us an opportunity to look for clusters in space and time, or vice versa, or in both. And the easiest approach is to try to use what is available. So the collaboration has decided to create an app for smartphones. In this case, with this app, the smartphone can be used as a very basic cosmic rays detector. And the big advantage is that everybody has a smartphone around, and they are already placed over the world. So this is how this has started, just by having the first approach, the usage of smartphones. So the information that is collected in the smartphones is concentrated in a supercomputer here in Krakow, and later is used for analysis of different type of reconstructions and so on. This is the app that is available basically for every smartphone, both in Android and iOS, and the type of traces that can be detected with the smartphones are simple lines. The smartphone has to be covered, so the regular light will not reach the camera, and only the cosmic rays will leave this kind of traces. This kind of traces have to be processed. They have to be processed like with different approaches, like machine learning, in order to distinguish whether this is an authentic, genuine detection or is just rubbish. Now there are many of these smartphones already distributed on the planet, so we have information, but we want to go beyond that, because obviously the smartphones have many limitations, from the technical compatibility of the software with different types of smartphones, to the limitation in resolution, in time, and of course in space. So that's why we are attempting to connect more the different type of detectors, more dedicated if possible, and also being in touch with the already existing proper facilities, like the most powerful, like the Auger Observatory or the telescope array. Things that we can try to study if we really are able to detect a huge cosmic ray ensembles are things like the space-time structure, because we can test whether there's a delay on the arrival of photons that will tell something about the scale of the space-time smoothness or granularity. We can also consider the existence of a Lorentz invariance violation, which in one hand, the theories of quantum gravity deform the Lorentz invariance in a way that it can be seen as a violation to standard Lorentz invariance. But also extensions of the standard model also predict, by expanding the symmetry group, that there could be Lorentz violations. So this can be also studied, because in many of these cases, the dispersion relations of photons are modified. For instance, in this work that I'm citing here, the authors come with a square root with a photon dispersion relation that is not linear, but is more like to the square root or something like this. So then there's a chance by looking at this at the cosmic ray showers whether this effect exists or not. Also, if we study different processes in cosmic rays, if the fundamental constants change in different regions of space-time or in different times, this could be some different interplay between those constants. And I give you here a reference for this small article where I have searched for some of these and some of the ideas where these variations of the fundamental constants could be sought. Then we have the pre-shower scenarios that I already mentioned, that the photon can interact with the magnetic field and create pairs, and this could eventually create this cosmic ray ensembles. Similarly, if there comes a supermassive particle unknown that was created in the early universe, it might interact and create showers by losing energy with collisions with photons or with the magnetic field as well. So the cosmic ray samples can be characterized by the width, either in space or in time. So here are 4 possibilities, for example, with the delta x small, with the delta t small, and then the other combinations, for instance, to the far right, delta x large and delta t large. So it's interesting to have a look at. There's other ideas, for instance, the possibility of photon splittings are around compact objects. So if there's a very energetic photon, it might interact again with the magnetic field, and according to some works from the 90s, there might be some a channel that where the photon splits. Otherwise, it's expected to
David,
do
2 minutes.
All right. So on the other hand, we want to connect with the multi-messenger astronomy, and if we are thinking about dark matter, perhaps compact objects are the place to look at. And nowadays, with the future interferometers, we can detect gravitational waves from different modes of these compact objects or from their mergers. In case of mergers, if dark matter may exist in halos or in the core or all over the neutron star or the compact object, and the gravitational waves may have information about it. So this is also interesting. In Europe and as well as in other places, the new interferometers will have more sensitivity. For example, take the case of the Einstein telescope, where we are already getting involved by the construction of this dedicated interferometer. Related to the interferometers, also there's seismic data that is important for them. But in this case, in the case of CREDO, we have used the seismic data for another study. We are trying to search for a relation between the cosmic rays and the seismic motion in order to ideally look for a precursor, a way of finding a precursor for
David,
earthquakes.
time is over. Can you please summarize?
All right.
Time for some discussion.
Yes. So I will just leave you with this. So there has been some studies of a correlation. If you want to look at the details, it's in a publication here. And we want to invite everybody to participate with us. If you have different type of detectors, there are many possibilities. And also with any kind of different approach to the multi-messenger astronomy. Thank you very much.
Thank you, David. Okay. Any questions or comments on this very interesting presentation? Ralph.
So, David, it's very interesting what you showed about the distributed, using the mobile phones. Is it, did I read this well? It's really like so many users already, or was it just the plans that you showed?
Yeah, what I show is the total number of users. Of course, they are
Like
not
10
working.
million or what?
Yeah. But this is global. During the since 3-4 years of this project, people have been connecting and disconnecting. But this is more or less what is when you add all this information. This is what we have. Of
So
course,
it's a cumulative number. Okay, yeah.
yes.
Because
But in principle, at every moment there's some smartphones there that are detecting, and I have to thank like educational institutions and also scientists and amateurs that have been helping with this.
yeah, that's very impressive. Thanks. Yeah.
Okay, over there.
Yeah, thanks. It's interesting, lots of interesting ideas. One of the things I was wondering, since you've had so many smartphones working already, is there some kind of engineering array run where you would try to show us some reconstructed events of those? So is this still not dense enough to get to a point where you can actually show that this concept really works?
Yeah, we have some results. The data is being processed, but at the moment, one of the challenges is that it's not uniform because of different models with the smartphones, and that one of the greatest needs is to also have it in connection with a bit more dedicated detectors, so we will have a reference, let's say. So I will say that we are getting there, but not yet to say that if an event like this happens, we will be able to be for 100% for sure that it was like this, but we are trying to get there.
Yeah, I can add a comment to that. It was actually kind of tempted back in Krakow to have an assembly of several smartphones together to try to see if there is any kind of possibility to see extensive showers. But again, as David said, it's quite complicated to perform.
Okay. Any other question or comment? Oh, over here. Yeah. Please go ahead.
Very interesting experiment. How can you reach timing resolution to reconstruct events? Or what are your requirements of timing resolution to observe the events?
Yeah, so basically we are limited by the resolution of the smartphones, and depends on what phenomenon are we studying is whether we have it within reach or not. And that's why our need to connect also more dedicated detectors to try to improve or to double check. For instance, in the case of the study of the cosmosismic correlations, we not really need a high resolution, because if there's some seismic event and the cosmic ray flux is disturbed, then it's more about having a proper global detections. On the other hand, if we have a very energetic process where the particles, where the showers go beyond the resolutions of the smartphones, we will not find it definitely. So, but since we don't know exactly what are we after in the case of dark matter, then still is worth trying and trying to use this data. If we find more applications, it's also possible. It's also worth to keep doing the research.
Thank
Okay.
you.
Okay. Thank you, David. Let's thank